All right, welcome back. So today we are going to be looking at the organic family known as aromatics. So these right here are benzenes and all our compounds that have benzene-like properties. So of course we're going to have to look at what benzene is and some of its properties as well, and why aromatics have their own classification. So aromatics are like cycloalkanes in that they are ring-shaped. However, they are believed to have a rotating bond. So there is no evidence for these double bonds actually existing. So when we draw it, there's going to be two ways of drawing it. All right, so we're going to go over here very shortly. So aromatic compounds are not considered to be saturated nor unsaturated. They're their own thing. This is why they do not fall within the aliphatic hydrocarbons. They are their own thing known as aromatics. So how benzene looks. Its chemical formula is C6H6. So we have 6 carbons in a ring like this. Now we have double bonds that go around like this. So this is how we get C6H6. So we have this 6 carbon ring around in a structure. Now you will notice that drawing cyclic structures as structural forms like this is a little hard sometimes. So what you will notice mostly it is line diagrams with the double bonds on the inside, just like this. I'm just going to fix this little double bond because it didn't look right. Boom. All right, so this is our benzene or our aromatic compound. Now in our line diagram, each point on this hexagon represents 1 carbon with 1 hydrogen atom attached, leaving a bonding electron at each carbon. So evidence indicates that all the bonds between carbon atoms are identical length and strength. So this is evidence that the 6 extra bonding electrons are thought to be evenly distributed in a line diagram. So kind of what we have like this is, we'll finish kind of drawing this one out. Right, so we have our carbon, 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 and carbon. And what happens is that we can imagine that the electrons here, so this kind of that lone pair that came from the bonding, is that it's moving around constantly. All right, so we have all the electrons are in steady movement going around. So this leads to, instead of having it static right here with all double bonds, sometimes benzene is represented like this, with this circle indicating rotating double bonds, or the electrons in that bonds just rotate around. So this is why they do have their own different family known as aromatics. And even when we get into reactions, they are not going to react the same way as alkenes or alkynes will, because of this rotating double bond on the inside. So of course with our aromatics there are 2 types or 2 ways aromatics are represented. So first of all, benzene or an aromatic as a branch. Now generally this is for larger molecules. It's going to be more convenient to consider benzene like a branch. So when this happens, of course, it's going to be called phenyl, P-H-E-N-Y-L. So notice it has that Y-L ending, indicating that it is a branch. Now you will notice that benzene is going to be considered a branch if kind of only one thing is attached to benzene and the molecule that you're looking at is kind of big, right? So for example, when we notice this molecule right here, we can tell that if we tried to have this as a parent chain and you tried to name this up here as a branch, it's impossible, right? Because it's not methyl, ethyl, butyl, propyl, or anything like that. So when we come into this situation, we find our longest continuous carbon chain, right, which is going to come around and up here like this. So our longest continuous carbon chain consists of 1, 2, 3, 4 carbons. Now, when we start listing what's carbon 1, what's carbon 2, and so on, we have to go back to our alkane naming, and that the first carbon is going to be the one closest to our first branch. All right? So when we look at this M right here, so if we start on this carbon and we go 1, 2, 3, 4, okay, so we can tell we have our first branch off carbon 2. Now, if we go the other way, oops, sorry, and we go 1, 2, 3, 4 this way, we will notice that, well, we get our first branch off carbon 2. So when you're stuck in a stalemate like this, you have to remember that the alphabet is going to take priority. Priority. So we look here, we have this one up here is methyl, and this one down here is phenols. And you got to ask yourself which one comes in the alphabet first, M or P. So you can sing the alphabet song, you know, A, B, C, D, E, F, G, H, I, J, K, L, M, and realize that, oh, methyl is going to get labeled first, right? Because M comes before P. And this is phenol. So when that is the case, we have to label this 1, 2, 3, 4, just like this. And we're only going to use this whole alphabet thing if we're stuck. So no matter what, our branches are on the same way possible. When we are labeling them, alphabet kind of wins out. So in this case right here, we'll have our 2-methyl, 3-phenyl, and this right here, butane. All right. Now, even our next example right here, so if you want to try this one on your own, please pause the video, and if not, I'm just going to go through it right now. So just like before, we find our longest continuous carbon chain, which in order to do that, we have to start at a carbon down here. We are going to go along this way and up here. Now, I could have went down the other way as well. We would have had the exact same thing. But anyway, this is my longest continuous carbon chain. Now, when I'm trying to figure out what is carbon 1 or what is carbon 2, I'm going to have to start at either this end right here and go 1, 2, 3, 4, 5, 6, or I go the other way. Now, if I go this way, my first branch is off carbon 3. So I'm going to erase those and label the other way. Oops, sorry, I didn't mean to erase that much. There we go. So I'll go 1, 2, 3, 4, 5, and 6. Now notice this time my first branch, so this methyl is off carbon 3. Carbon 2. So 2 is a lower number. Therefore, how I have it labeled right now is perfect, where I have my methyl branch and my phenyl branch. So the name for this, when we put everything together, we can tell that, and luckily this one here, it just so happens it works out that methyl comes first in the alphabet, and we're going to label it first again. Right, but this one, the alphabet did not influence our decision to label this one up here as carbon 1. It's because the first branch is there. So we have 2-methyl, 4-phenyl, sorry, forgot to put in the dash. 4-phenyl, and then of course we have hexane, because there is no double bond or triple bond. All right, let's move on to the next. So of course these are drawing, same thing as before. I'm gonna let you guys pause the video here if you want to, and then of course draw them, but I will put the answers up in 3, 2, 1. And here are the answers. So you will notice I drew benzene differently in both cases right here. So we have the 3 double bonds, and here we have the circle. It doesn't matter which way you represent it, you're going to see both. All right, so you're going to choose whichever one you like most, and then write them how you want to. All right, and that should be our 2-phenyl pentane right here, and of course our 3-phenyl 4-propyl octane. Now, benzene as the parent. So this is the other option for benzene. It's not a branch, it's a parent. Basically, it only has one branch attached. So if one branch attached, name the branches as before, like alkyls, with benzene as the name of the parent chain. No number is necessary for one branch, just like our cycloalkanes. All right. Now, if there's more than one branch off benzene, then this is how you know it's going to be a parent. If there's more than one branch or just one simple branch, then number them to get the lowest numbers possible, just like we did for our cycloalkanes and cycloalkenes. And of course, list alphabetically, just like we've been doing before, with benzene as the parent. All right. So for example, when we look at our first one right here, we can tell that benzene must be the parent because we have multiple branches off benzene. Now, we can list these here as well. So these are all methyl branches, which is okay. Now, as for numbering our benzene ring, what we're going to have to do is we're going to try to get the branches in the lowest numbers possible. So that means obviously carbon 1 is going to have to show up on a branch. So there's many different ways to kind of go about it. We can, trial and error is kind of the best. Like if you go 1, 2, 3, 4, 5, 6. So we get branches off 1, 2, and 5, right? That could work. However, I am not going to just do one way and then that's it. I am going to check to make sure I can't get lower numbers. So if I go this way, 1, 2, 3, 4, 5, 6, well, notice now I get branches off of 1, 2, and 4. 1, 2, and 4 are much lower than the other way I had previously, which was 1, 2, and 5. So because of this, this is how I need to label it, because I have my branches off lowest numbers possible. So therefore, the name for this one, I'm going to get 1, 2, 4. There are 3 methyls, so we go trimethyl, and then the parent name, benzene. All right, so the next one, I'm going to let you try this one on your own, so please pause the video, try it, and then I'm going to put the answer up in, once again, 3, 2, and boom, this is what we get. So we have 1,3-dimethyl-4-propylbenzene. Of course, because of this here, no matter what, you would have had, oh, this shouldn't be 4. Crap, I got to stop doing this. I keep putting in the wrong answers. This is 5-propylbenzene. So no matter where you look at it, you would have had branches off 1, 3, and 5. Of course, because methyls come first in the alphabet, we want to put them as 1 and 3 first, and then propyl, because there's 3 carbons, goes last. Now, as for the drawing, same thing. Please pause the video, draw these out, see if you get the same answer, because I will put the answers up now in 3, 2, 1. And we have our drawings right here. So same thing, you'll notice I used a combination of the 3 double bonds and the circle. It all means the same. So as you can tell right here, we have our ethyl off carbon 1 and 3-methyl, and same thing, 1-ethyl, 2,4-dimethylbenzene. I believe that is it. So we have a few, these are old diploma questions. So please pause the video right now, have a read this one, answer the question, because I'm going to put the answer up in 3 seconds. All right, and the answer for this one here is B. Now, of course, this right here, it's going to help out if you draw it out, okay? And the reason for that is when we look at our things, so which of the following rows identifies the total number of carbon-to-carbon covalent bonds in a single butane molecule and the classification of butane? So, of course, we need to draw out butane, right? So butane is C4H10. Now, once again, you don't need to do structural, but it does help to really view what's going on. So when we look at the amount of single carbon-to-carbon covalent bonds, we have 1 bond, 2 bond, 3 bond. So there's 3 covalent bonds within this molecule. So that's how I knew this answer should have been either answer A or B, right? So I could have easily scratched out C and D. Now when it came down to if it's unsaturated or aliphatic, unsaturated, remember, this means double or triple bonds. Of course, butane, alkane, it doesn't have that, so I know it can't be A, therefore it must be aliphatic, which by definition, aliphatic is just hydrogen and carbon. All right? Now the other one, same right here, so the organic compounds above that are isomers of nonane, so C9H20R. So we have 3 different molecules, same thing. Pause the video, try this one out, and I'll put the answer up in 3 seconds. And the answer for this one is C. Now, you could have easily drawn these and done your counting, which is fine. That is one way to do it. Another way to do this is if you remember the general formulas for all of our alkanes, alkenes, cycloalkenes, cycloalkanes, alkynes, cycloalkynes, basically all of our aliphatic stuff. This will really help you because remember this formula right here, it is nonane. It's in the formula of CnH2n plus 2. And all alkanes have this formula. Now, if you remember cycloalkanes had the formula of CnH2n. So therefore, if we had a cycloalkane, like our first example right here, 1,2,4 trimethylcyclohexane, if you count the number of carbons, it's still going to have 9, but because it's a cycloalkane, it's going to come in the formula of CnH2n, so the empirical formula here is going to be C9H18. All right? So therefore, it cannot be 1. Now, as for 2 and 3, if we count the amount of carbons, so we have pentane right here, so that means there's 5 carbons, and then we have tetramethyl. So tetramethyl means an extra 4. So we got 5 plus 4, and that's 9. But because it's not a cyclic compound, this is going to come in the formula of CnH2n plus 2, or C9H20. So that one works. And same thing, if we count all the carbons here, we got 3 ethyl, so this is 2 carbons. We got dimethyl, so that's another 2. So 5 carbons here from our branches, and then pentane, our parent chain has 5, or sorry, 2 and 2 is 4, right? So 4 carbons here. And then our pentane is 5 carbons. That is equal to 9 carbons. And it's not cyclic, it's all straight chained, so it'll have the same formula of C9H20, so that's why the answer is C. All right, so 2 more, same thing, so please pause the video because I'm going to put the answer up in 3 seconds. And the answer for this one is C. Now, for this one right here, there's no other way around it. There's no quick way to actually figure this one out. You're given line formula for a reason, because as I mentioned in class before, is that with line formula, it's very hard to predict how many hydrogens are present. So that's why this question exists. We know myrcene is C10H16. Now, if you count the carbons in all these compounds, there's going to be 10. All right, so the difference right here is going to be the number of hydrogens. So that's where you just have to go through and count the number of hydrogens. So I'm just going to place a number, and it's going to be in pink, on how many hydrogens are on each carbon based on the bonding capacity. All right, so this is where you have to count the number of lines going into each point. All right, so for example, in A. So at the end right here, we'll notice that there's 3 lines. So that means that this carbon right at the end can take 1 hydrogen. Now this carbon right here, even though there's no bend, just because the triple bond ends, there is a carbon right here. Now if we count the number of lines, 1, 2, 3, 4, this one takes 0. Okay, so likewise, when we go to our third carbon right here, we can tell that there's 2 bonds going in, so it already has 2 bonds, so it needs 2 hydrogens to fill its slot, right, to fill its bonding capacity. Now the one right here in the middle already has 1, 2, 3, 4 bonds in there, it can't take any more. Right, so 0. Now when we look at the end carbons here, this one is going to take 3, this one takes 3. Because they're at the end, there's only 1 line, so it needs 3 hydrogens to fill that bonding capacity of 4. Now for our double bond ones right here, we can tell this carbon already has 1, 2, 3 bonds going in, so it could only take 1. Likewise, this one could also only take 1. Just because of the bonding capacity. Sorry, that's kind of looking a little weird. That should be a 1. 1. And of course, this one right here, we got 2 bonds going in there, so it can take 2. This last carbon only has 3 bonds going in, so it can take 3. Now, when we add up our numbers here, 1 plus 0 is 1, plus 2 is 3, plus 0 is 3. Then we have 6, plus another 3 is 9, plus 1 is 10, plus 1 is 11, plus 2 is 13, plus 3 is 16. So you got C10H16. Now, you're going to have to go through this with all of the other ones just to kind of make sure. All right? Now, if you do have any trouble with this particular section, just please email me, and I can probably send you a quick little video of me going through and counting all the ones here, or try redrawing them in structural formula, putting in all the hydrogens and count for yourself. And finally, last but not least, the number of carbon-to-carbon double bonds in myrcene is, and of course we have this one right here. Now this right here, it's going to be hard to draw out, but I'll put the answer up in a second and just go over it. So the answer is going up in 1, 2, 3. All right, so the answer here is C. Now, how this works now, it will help kind of drawing it out and then, figuring out the unsaturation. But I'm just going to go over to another page here and just kind of show you. So our general formula was CnH2n plus 2 for an alkane. So for myrcene, if it was just no saturation whatsoever, so fully saturated, we'd have C10H22. Now, that is kind of, it's an isomer of decane if that was the case, but you know we have C10H16. So when we look at what happens when we go from an alkane to an alkene, so we lose 2 hydrogens to create a double bond. We go down to the formula of CnH2n, right? So we lose 2 hydrogens, and we get C10H20. So this trick to this question is kind of going down to see how many on, so we have unsaturated, oh sorry, this is saturated, right? So this one here is completely saturated. And we just unsaturate 1 carbon by sticking in a double bond. Now our next one, if we go down, right, so lose some more, so CnH2n minus 2. Now this was our formula for an alkyne, or another way to think about it, that would be a formula for something with 2 double bonds, and we get C10H18, right? So we got no double bonds. We got 1, sorry, that's an ugly looking one. I'll try to make it a little. 1 double bond. Here we got 2 double bonds. So our next one, if we go Cn, if you notice the trend that's going on right here, we go CnH2n minus 4. So give us our C10H16 or 3 double bonds. And that's how we get that. So that's why our answer was, oh crap, I gotta stop doing this. It's not C, it is B. All right. So I tried to just answer that one off the top of my head, and I should have done this out beforehand. So we got no double bonds, C10H22, 1 double bond, C10H20, 2 double bonds, C10H18, and finally 3 double bonds, C10H16. So whenever we create another degree of unsaturation, we have to lose 2 hydrogens to do so. And that will give our answer as B. Man, I swear I'm going to stop making mistakes eventually. And of course, that brings us to our next chapter. So hydrocarbon derivatives, we'll worry about that next week. So anyway, just make sure to keep up on your workbooks. And remember, if you have any questions, do not be afraid to email me as soon as possible. I will get back to you in a timely manner. And hopefully we'll set up some time to do our live stream so I can help you guys with your workbooks or anything like that. All right. See you guys later.